Okay, so for Chapter 3, Section 8, we're going to be talking about composition and composition of molecules or formulas. And it's important that we appreciate, when we talk about composition, we're largely going to be talking about percent. We will also use ratios. So the percents that we're going to be talking about are percent by mass and percent by volume. There's a third percent, which we won't get into right here, that's used by chemists a lot. And then ratios, as I said. Mole ratios, I think, is the only ratios we're going to be doing. So first of all, let's consider, suppose you have a room. And in your room, you have a bunch of women and a bunch of men. And I really just want to talk about what is meant by the term percent, right? So, percent. And by the way, this can almost always be distilled down to a part. Can you read my writing? Per whole. Okay? Now, if you're going to do it as a percent, though, it's got to be times 100. Right? So, a part per whole. Now, if I say I've got a bunch of men and women in a room, and the question might be how many, just one second here, I put this in your worksheet. Let me look at that worksheet again. Put that in your worksheet, and the worksheet question was, I'm getting there. Suppose you have a classroom that contains 12 women and 8 men. Calculate the percent of women in the room, okay? So this is a symbol that we oftentimes use for women. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? So the number of women is equal to 12. Number of men is equal to, I need another symbol for that. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8. All right, so what's the percent of women in the room? Well, the percent is going to be the part per whole. The part is the women, which is 12. And what is the whole? The whole is 20, right? Okay. So what's the percent women in the room? It looks like it's 12 divided by 20, which is 6 over 10, which is equal to 0.6, okay? But now if we're writing this as a percent, then we've got to say that this is 60%. And can you see that's where I got my times 100? Okay, so 0.6 or 60% is how many women I have in the room. Now it's important to appreciate at this point what we mean by part and whole. And the part, I guess I just want to use the terms in context, and perhaps that's enough. I don't really want to define them, I think, at this point. But I do want to say that when we talk about percent of people, then it's going to be a number, right? Not a mass, over a number, right? It is not going to be a mass over a mass. We would never say, you know, how many pounds of women do we have in this room, or how many pounds of men, or how many pounds of people. That doesn't make any sense. We would never talk like that. We would say, what is the number of people we have in this room? Okay, but when we're dealing with chemistry and dealing with molecules, we are going to be talking about masses, because that's how we count, right? We're going to be counting with balances and scales. So let's do another example, and we'll sort of warm our way up to the masses. Let's suppose now in another example, we have a bunch, let me use the example from your worksheet. A grocer has 12 pieces of fruit. Now I've only drawn 1, 2, 3, 4, 5, 6, 7. I've only drawn 8 on here, okay? But let's say that we have 12, and the question is there are 7 apples. The number of apples is equal to 7, and in this scenario, there's 12 total. Number of apples plus watermelon is equal to 12. What is the number of watermelon, by the way? Okay, can you see that it's 5? right? How did I get that? Well, I took the total and I subtracted from it the one element and I got the other element, right? Okay, you can do that in your head, but we're going to be dealing with numbers sometimes that you can't do in your head, so it's important to appreciate really what's going on. So calculate the percent of apples. All right, now if percent is equal to part over whole, then part over whole, then, and of course if we're gonna put it in the form of a percent, we've got to say times 100 times 100, right? What's the part here? And the question is calculate the percent apples. So it looks like it's going to be 7 over 12 times 100, right? All right. So 7 over 12 times 100. Now, I can't do that in my head. I'm going to go over here to my calculator. 7 divided by 12. And it looks like that's 0.5833. 0.5833. Repeating, right? How many sig figs in this number, by the way? 7. How many sig figs? It's an exact number, right? Because we're talking about the number of apples, right? How many sig figs in that number? Infinity. So we're going to say repeating here to say that that's the fraction. Now this is, we haven't times by 100 yet. We've got to say times 100, which is equal to 58.33 repeating percent. Okay, that's the percent of apples. Now we've got seven apples and 5 watermelons. Okay, but I think it's now watch this. We're gonna ask a different question. Now we're gonna say, what is the percent by mass? What percent by mass? You see, I've got 58% apples. Let's see, again, number of apples is equal to 7. Number of watermelon is equal to 5. Do you think that we've got more apples than watermelon? Well, we do if we're doing by number, but what if we do by mass? So I think what I did in order to get this number here, I think I Googled what's the average mass of an apple. Average mass of an apple is, got a phone call coming in, and I need to not take this because I don't know who it is. I'm going to, all right, so I Googled what was the average mass of an apple. The average mass of an apple is equal to, I'm going to skip this phone call because I don't know who it is. And the average mass of an apple is 110 grams, okay? And the average mass of a watermelon, of course, this depends on what kind of apple it is and what kind of watermelon it is, of course. But this was 9,100 grams. Wow. Okay. So what I'm going to do now is I'm going to say my mass of this is per apple, and this is per watermelon, okay? But the mass of apples total is going to be 110 times 8, right? This is going to be 880 grams of apples. Okay? Now how many grams of watermelon do I have? I don't know why this put this in parentheses, but let's go ahead and do that too. How many grams of watermelon do I have? Well, it's 9,100 per watermelon, and I've got 5 watermelons, so it's going to be 9,100 times 5. 9,100 times 5. Wow, okay, a lot of watermelon. 45,500 grams of watermelons, okay? Now, if I do percent by mass, then I've got to take my part is going to be, let's see, what was the question again? What was the, calculate the percent of apples now. And the percent of apples now is going to be, if it's percent by mass, wow, big difference. It's going to be 880 grams of apples over 4,500 grams of water, plus 880, right? Grams of apples, because it's got to be the total, the whole. So, just a second here. plus 880 is running out of space here. This is going to be 880 over 46380. Okay, 880 divided by 4680 comes out to be, this comes out to be 0.01897 times 100, right? Because this is going to have to be times 100 because it's percent. And so this looks like it's going to be 1.897% of apples. Wow. Are you sure about that? Yeah. Oh, yeah. Wait. No, it's not 880. He only had 7 apples. Look at that. Did that bother anybody? Look at that. 7? No, it's not 880. It's 770. Okay. 770. Oops. 770. This numbers are bogus. All right. So much for my nice, clean explanation there. 770. 770. That's even less. Huh. This comes out to be 1.66% of apples. Okay? Is that possible? Yeah, because this is almost 10 times as much. Sure it is. Okay. 1.66%. Something's wrong with that. Something's wrong with that. That doesn't make any sense. Yeah, it's almost 100 times. Yeah, it does make sense. Okay. It's almost 100 times as big. Is that right? All right. Are apples really that small compared to watermelons? 100 apples? That's a little hard to believe, but let's suppose it's true. Okay, the math is good. It's hard for me to believe these numbers here. I may go back and redo that. All right, let's suppose that that's true. Since that's what your worksheet says, we're going to go ahead and say that's a lot of apples in one watermelon. A little hard to believe. Okay, so it looks like if the grocery is doing percent by mass, it's 1.66%, and if it's percent by number, it's 58%. What a big difference. What a big difference. Okay, so it looks like our math is good there. The conclusion is a little hard to believe, but you can see that you're not going to get the same number if you're doing percent by number as you are if you do percent by mass. Okay, let's go to another example here. Calculate the mass percent of chlorine in Freon 112. Okay, so the mass percent. So I'm going to set this up before I even start, and the mass percent is going to be the mass of chlorine over the mass of Freon 112 times 100%, and that's going to be my answer. Okay, so this is going to be the percent of chlorine. Do you see that? Because I've got my part, which is the mass of, this is my part, and this is my whole. Okay, so what's the mass of a chlorine atom? The mass of a chlorine is equal to 35 point, I don't even know, 45, I think. I'm going to look that up. My periodic table, from my textbook, 35.45, that's right. 35.45 AMU, or grams per mole, it doesn't matter in this case, right? And then the mass of Freon 112 is going to be 2 times carbon plus 4 times chlorine plus 2 times fluorine. Carbon's 12.011. Chlorine is 35.45. And fluorine is what? 19.00, is that right? Okay. 19.00, which is equal to 24.022, plus I can't do that one in my head. 2 times 4 times 35, 35.45, it's 141.8. Is that right? Yep. Plus 2 times 19, which is 38. Okay. Plus 38 gives 203.822. 203.822 AMU, right? And now I'm ready to calculate this. This is 35.45 AMU. This is 203.822 AMU times 100%, which is equal to 17.392 percent chlorine. All right. Okay. Oh, you know what I did? This is not correct. I've got 4 chlorines in there, not 1. Wow, classic mistake. This was a Freudian slip here, folks. This was a mistake. I don't have just 1 in there. I've got 4 of them in there, right? Look at that. The mass of chlorine is going to be 4 times each of those. Wow. Okay. So this ends up being 4 times that, which is going to end up being 4 times this. Times 4, which is 69.57. Wow. 69.57%. Did you catch my mistake before I did? Wow, look at that. If you did, pat yourself on the back. You're thinking very clearly. Okay, so it's 69.57%. And I just want to think about this one more second before I move on. 69.57%. Is that right? Okay, looks like it is. Okay, last thing I want to do is sig figs. And this looks like it's got 4 sig figs in it. This has got 4, 4, and 5. Okay, so yeah, we're going to have 4 sig figs in our answer. So this is correct. Okay, very good. All right, let's do another example. Hydrogen may potentially be used in the future as a fuel to replace gasoline. There's a couple problems with it, but most major automobile companies are developing vehicles that run on hydrogen. These cars are environmentally friendly because their only emission is water vapor. Nice. One way to obtain hydrogen for fuel is to use an emission-free energy source such as wind power to split hydrogen from water. All right, so far, this appears super interesting, but has nothing to do with the question. Nothing to do with the question. What mass of hydrogen in grams does 1 gallon of water contain? Okay, so what mass of hydrogen in grams does 1 gallon of water contain? So what I'm going to do, kind of think about this, mass, grams of hydrogen, 1 gallon of water. So the volume is equal to 1 gallon of water, or 1.00, which I'm going to convert this to milliliters because I'm given mils here, gallon to liters, liters to milliliters, right? And I'm going to look up how many gallons are in a liter. I think that's in the back cover of my textbook. Back cover of my textbook, volume 1 gallon is equal to 3.7854 liters. 1 gallon is equal to 3.7854 liters. And then there's 1,000 mils in a liter. And so look at these gallons cross off, these liters cross off, and I can do this in my head. That's going to be 3,785.4 mils. Okay, so that's how many milliliters we have. And we know that the density of water is 1 gram per mil. And so mass is equal to density times volume, right? So 1 times that, you see the mils are going to cross off. This is going to give me 3,785.4 grams, okay? That's the mass of water that I have. Okay? If that's the mass of water that I have, then what I'm going to say, this is H2O. The question is, what mass of hydrogen do I have in this? I'm going to go back and do a problem like I did previously. We're going to find the percent first. So the percent of hydrogen in water, this is going to be just like the problem we did in the previous slide, except hopefully I won't make that mistake, is going to equal to the part whole times 100%. And the part is 2 times hydrogen, right? Over the formula weight of water, which is 2 times hydrogen plus 1 times oxygen, because it's H2O, times 100%, right? And hydrogen's 1.008, 1.008, and this is 16.00, and so the percent of hydrogen in water is 1.008, just a second here, 1.008 times 2 divided by 2 times. Okay, so it looks like it's 11.19%. All right, and so what we can say is 11.19%, look at this. This times 11.19%, wait, there's 3 ones there, equals the grams of hydrogen, which is equal to what? Times 3,785.4 equals 423. 423.588 grams of hydrogen. All right, so you see what I did? I found the percent of hydrogen in water. I first of all found the mass of water. Then I found the percent of hydrogen, and I multiplied that. That's my fraction of it, right? That's sort of it. I took away the percent sign and just made it a fraction. All right, is equal to that. Now, how many sig figs do I have? I've got 3 sig figs here, 3 sig figs here. So this is going to have 3 sig figs, which is going to equal 424 grams of hydrogen. All right. So hopefully that's